Okay, so thanks a lot for the introduction, and I would like to thank the organizers for the invitation. It's a great honor to be here. I'm going to be speaking about joint work with Elia Brouet from Università Bocconi in Milan and Aaron Neighbor from the Institute for Advanced Study in Princeton. Subject is conjecture raised by Milnor in 1968. Which predicted the following. So the conjecture predicted that if M, N, G is a smooth, complete Riemannian manifold with a non-negative Ricci curvature, then the fundamental group should be finally degenerate. Okay, so let me start by briefly reviewing the state of the art around the conjecture. Okay, well, for n less or equal than 3, the conjecture is known to be true. If n is equal to 1, there's not much to say. If n is equal to 2, the result goes back to work of Kohn and Vossen in 35, who actually provided a quick classification up to diffeomorphism of manifolds with non-negative Ricci curvature, which in dimension 2 is the same as having non-negative Gaussian curvature. Okay, in dimension 3, it took some more time. First, Chen and Yao in 82, they completely classified the complete manifolds with the strictly positive Ricci curvature, and as a corollary of the classification statement came the solution of the Milnor conjecture in dimension 3. And later this was extended to the case the conjecture is dealing with, so the case of non-negative Ricci curvature, more recently by Liu in 2013. Okay, so for n equal to 4 or 5, the conjecture is still open. Okay, and quite remarkably, it's still open even in the case where you strengthen non-negativity of the Ricci curvature to Ricci flatness. Okay, and for n less greater or equal than 6, the conjecture is false. Okay, and this is due to the following theorem that we proved together with Brouet and Neighbor 2 years ago, saying that if n is greater or equal than 6, there exists a smooth, complete, n-dimensional Riemannian manifold satisfying all these conditions, so with non-negative Ricci curvature, and let me drop all the other properties. So smooth, complete Riemannian with Ricci greater or equal than 0, and fundamental group isomorphic to the group of rational numbers modulo 1, which is clearly an infinitely generated group. Okay, so before I move on, let me also stress that the conjecture, so several people worked on the conjecture in the past 50 years, and the conjecture was known to be true in several circumstances under additional assumptions. For instance, Chigger and Gromov, and later with a different proof, Gromov established the conjecture where you strengthen the assumption that Ricci is non-negative to the assumption that the sectional curvature is everywhere non-negative. There have been partial positive results under conditions about the volume growth of this manifold. So if a manifold has non-negative Ricci curvature, then by the Bishop-Gromov monotonicity formula, we understand that the volume can grow at most like R to the n, the volume of balls. And it's known that if the volume growth is maximal, then the fundamental group is finite. Calabi and Yao, on the other hand, proved that the volume of such manifolds, whenever they are non-compact, must grow at least linearly with the radius. And if it grows exactly linearly, then Sormani proved that the fundamental group is finely generated. And more recently, there has been a series of other results connecting finite generation, so proving the Milnor conjecture under some assumptions on the so-called asymptotic geometry of the manifolds. Okay, so the next point that I would like to address is concerning the choice of the fundamental group in the counterexample. So I would like to justify why choosing the rationals modulo the integers is a natural choice for the construction of a counterexample. Okay, and in order to do that, it's worth recalling two theorems. So the first one is due to Wilking in 2000. Proved that if M and G is as before, then phi 1 of M is finally generated if and only if every abelian subgroup gamma of phi 1 of M is finally generated. Okay, and people have often phrased this theorem of Wilking by saying that if there exists a counterexample to the Milnor conjecture, then there must exist one whose fundamental group is abelian. Okay, so this is the first restriction. And the second restriction I would like to point out is due to more recent work of Kapovic and Wilking. 2011, prove the following. So for any n greater or equal than 1, there exists a constant C of n, only depending on the dimension, as the demonstration suggests, such that if M and G is as before, and gamma is a subgroup of the fundamental group of M, which is finally generated, then gamma can be generated by at most C of n elements. Okay, so this is putting a strong restriction on the structure of any finitely generated subgroup of the fundamental group of a complete manifold with non-negative Ricci curvature. Okay, let me argue that by combining these two statements, so it's fair to say that the simplest possible options for the fundamental group of a counterexample to the Milnor conjecture are either Q mod Z or Q. So the rationals modulo the integers, the rationals or their subgroups. Okay, why? Well, of course, they are abelian. Okay, and what happens if you look at finitely generated subgroups? Any finitely generated subgroup of Q mod Z or of the rationals is cyclic, generated by just one element. Okay, so it satisfies this statement with the smallest possible constant. C of n is equal to 1 in this case. Any questions? Okay, so about the algebraic structure of the possible fundamental groups, here is an open question. So as far as our construction is concerned, we can only realize abelian infinitely generated fundamental groups up to finite index. Okay, and an interesting question which is open is whether one can push the construction to realize genuinely non-abelian fundamental groups for counterexamples. So a very concrete statement, a very concrete proposal might be the following. So let gamma be the group of upper triangular 3 by 3 matrices with ones on the diagonal and coefficients A, B, C, which are either rational or rationals modulo 1. Okay, so this group is not abelian, it is nilpotent of step 2, okay, and it is open whether one can realize such a group as the fundamental group of a complete Riemannian manifold with a negative Ricci curvature. Okay. So I spent the remaining time giving you an outline and so discussing some of the ideas that enter into the construction of the counterexamples. Okay, so. Okay, and for notational simplicity, what I'm gonna do is I'm gonna construct a complete 7-dimensional Riemannian manifold whose fundamental group is isomorphic to the so-called dyadic rationals, modulo the integers. Okay, so my goal is to construct M7G with Ricci greater or equal than 0 and pi 1 of M isomorphic to the so-called dyadic rationals mod 1. Okay, so what are the dyadic rationals? These are the rational numbers that can be written with a denominator which is a power of 2. Okay, and I'm dividing by z. Okay, so you can view this group as a subgroup of the original Q mod z, which was appearing here. Okay, why am I focusing on such group? Because the notation is going to be simpler. Okay, but the ideas that I'm going to illustrate work almost in the same way for the case of Q mod z that I stated here. Okay, and also rather than building the manifold itself, I'm gonna argue by constructing its universal cover together with the smooth, free isometric action of this group. Okay, so actual goal is gonna be building M7 bar G bar with, so simply connected with non-negative Ricci curvature and the free isometric action of gamma, where from now on I'm gonna denote by gamma this group that I introduced here. The rational numbers, the dyadic rational numbers modulo the integers. Okay, so before I get into the details of the construction, so let me make an elementary algebraic observation. So, okay, I'm going to denote by little gamma I to be the element of this group gamma corresponding to 1 divided by 2 to the I. Okay, so the order of such guy is 1 it's 2 to the I. Okay, and I'm gonna denote by capital gamma I the subgroup, the cyclic subgroup generated by such guy. Okay, and it's completely elementary to check that if I take the union for I running in the natural numbers of gamma I, okay, then what I get is all of the group. Okay, and this is going to be important later. Okay, and the other important point will be that there are these generators, they are not independent. Okay, so what happens is that if you pick gamma I plus 1 and you raise it to the power 2, well, what you get is the generator that you got at the previous step of the construction. Okay, and this is true for any natural number n. Any questions on the setup? Okay, so before we get to the construction of the counterexample, I would like to get you in the right mindset. I would like to discuss the construction of a toy model. Okay, and what I'm going to do is I'm going to discuss a classical construction of a proper isometric action of the group gamma on a metric simplicial tree. Okay, and I'm going to adopt two slightly different perspectives on the construction. One is global, let's say, and the other one is an inductive construction, which is the one we are going to follow when it comes to the construction of this manifold. Okay, so let's discuss the model. Okay, and as I was saying, I would like to construct a space X, which is a metric simplicial tree. Together with an action of gamma on X, which is proper and isometric. Okay, and the construction is very simple. Okay, one starts from the half line, so gamma, the discrete group you're starting with. You take the cross product with 0 plus infinity, the half line. Okay, and then to get a tree out of this, you quotient it out by an equivalence relationship. Okay, where I stipulate that little gamma, little t is equivalent to little gamma prime, little t prime, if gamma to the minus 1 times gamma prime. Okay, and I'm gonna adopt both the multiplicative notation and the additive notation for the group gamma, which is clearly abelian. Okay, belongs to capital gamma I. So remember, capital gamma I is the cyclic group generated by this element of order 2 to the I. Okay, and then the second requirement is that the time components, they should be equal. They should be equal, greater or equal than I, which is, you should view as the step of the construction we are following. Okay, so how does the picture of this space look like? Okay, so the picture you should have in mind is something like this. Okay, where the elements, so the picture continues forever on the top and on the right, let's say, and the elements in the bottom row, they are indexed by gamma. Okay, the elements in the first row here, they are indexed by gamma, modulo gamma 1. Okay, and so on and so on. Okay, so and now I would like to endow this guy with a metric. Okay, and the metric I endow it with is the unique metric. So endow X with the unique length metric such that the inclusion of 0 plus infinity into x, so sending t into little the equivalence class of gamma t is in isometry. Okay, and on such space, I can define very naturally an action of gamma. So note that gamma acts on this product trivially by multiplication on the left on the first component. Okay, so gamma acts on gamma times 0 plus infinity by multiplication on the first component. Okay, and it's completely elementary to check that this indeed induces an action of gamma on the quotient space. Okay, so. Okay, and it's also straightforward to check that this action is isometric and proper with respect to the metric defined by this constraint. Okay, so let me now adopt the slightly different perspective that I was alluding to before, where instead of building straight away the global picture of this metric simplicial tree, I try to build this metric simplicial tree inductively. Okay, so inductive. Okay, and what you should have in mind is that at the ith step of this inductive procedure, what you are doing is you are running this construction, replacing gamma with the subgroup gamma I that I introduced there, and 0 plus infinity with the finite segment 0 I. Okay, so what happens, for instance, at the first step of the induction? So for I equal to 1, okay, what you're gonna do is you're gonna draw a picture like this. Okay, and how does the generator of the group gamma 1 act on this picture? So gamma 1, okay, is just gonna act by fixing the top vertex here and swapping the two sides of the tree. Okay, so it's acting like this. Okay, now what happens at the inductive step? So going from I to I plus 1. Okay, and let me draw the picture in the case where I is equal to 1. Okay, what you need to do is you need to pick two copies of the picture that you built at the previous step of the induction. Okay, so let me draw them here. So you pick two disjoint copies of what you realized at the previous step of the inductive construction. On top of those, you put a new vertex. Okay, you connect the upper vertices of the old pictures with the new one. Okay, and then I need to tell you how to extend the action of the old generator to this picture. Okay, and the old generator is gonna act by fixing the top part of the tree, and just as the original gamma 1 did on the bottom part. So gamma 1 is gonna do something like this. Okay, now remember gamma 2 with my notation as order 4, and how does it act? Okay, so the gamma 2 is gonna swap the two components, so it's gonna send this branch of the tree onto this branch of the tree. Okay, and it's gonna send this lower branch of the tree onto the first one by swapping it after it moves it to the place. Okay, and you can easily check that in this way, so the action is gonna be isometric. Okay, and all the algebraic relationships that I get between generators, they're gonna be satisfied. Okay, any questions? So now I would like to start from this picture, okay, and inspired by this picture, build the universal cover of a complete smooth 7-dimensional Riemannian manifold, and though with an isometric action of the group gamma. Okay, so starting from that picture, there are a few steps one needs to go through. So what we need to do is first turn the space X into a smooth 7-dimensional manifold, smooth, simply connected M bar 7. Okay, then I would like to, through this process, to make the action of gamma free. So the action that I introduced with this toy model is not free. Its property is isometric, but it's not free. So I would like to turn the gamma action into a free one. Okay, and eventually my goal is to make this action isometric with respect to a metric G bar on M bar, such that the Ricci curvature of this metric is everywhere greater or equal than 0. Okay, I'm gonna focus on the first two steps. Okay, and then I'm gonna give you some detail, not all of them, regarding this last step. Okay. So before we move to that, I need some prerequisites. Okay, which are going to be relevant, and I also need to set some notation, which is going to be very important when it comes to the definition of the action of the group gamma on my 7-dimensional manifold. Any questions? Okay, so I need to recall you what the op function is very briefly. So I'm going to be viewing S3 as the set of complex numbers such that Z1 square as a set of points in the complex two-dimensional space such that Z1 square plus Z2 square is equal to 1. Okay, and the observation, the classical observation is that there is a free circle action on S3, the so-called op function, where, so the action of an angle theta in S1, which I'm viewing as R mod Z, on a pair of such complex numbers, Z1, Z2. This is defined to be the multiplication by e to the 2 pi I theta of both components. Okay, and it's a classical exercise to check that this induces actually a smooth free circle action on the free sphere, and such action is isometric with respect to the standard round metric on S3. Okay, so. Okay, well, then at this stage I can introduce in a natural way an action of the two-dimensional torus on the product of two free spheres. Okay, so in this way I get an action of T2 on S3 times S3. Okay, where theta 1, theta 2 acts on a pair G1, G2 by op function on each of the two components. Okay, so theta 1 applied to G1, theta 2 applied to G2. Okay, and then I want to look at a specific family of circle subactions of this T2 torus action, which I can obtain in the following way. So I can consider the embedding of the circle into the two torus, where theta gets mapped to theta k theta, okay, for an integer number z. Okay, and so by composing this homomorphism with this action, I get a sequence of distinguished circle actions on the product of two free spheres, which I'm going to denote by 1k types circle actions. Okay, so in this way, okay. So now I got all the terminology and the notation for telling you how the inductive construction of this manifold works. Okay, and the idea is going to be to follow the second inductive approach on the construction of the metric simplicial tree. Okay, so what I'm going to do is I'm going to build a sequence M bar I together with actions of the group gamma I. Okay, this sequence is going to be built inductively, and next what I'm going to do is going to be focusing on the inductive step. Okay, and then, so I'm not going to focus on the last step, where starting from this sequence of, let's call them finite objects, one passes them through the limit to obtain the final object. Okay, so I'm going to let you be guided by this picture, okay, in comparison with the previous picture for the last step. Okay, so one has to build such a sequence, okay, and then formally pass to the limit. So let me start from the base step of the construction. Okay, so for the base step, I let M1 bar be the product of a three-dimensional sphere with a four-dimensional disk. Okay, so let me draw it here. Okay, and I'm going to be viewing the four disk topologically as the cone over the free sphere, just by using radial coordinates with respect to the center. Okay, and then I need to tell you how the generator of the group gamma 1 acts on this object. Okay, so gamma 1 acts by trivially on the radial direction of the four disk. Okay, and it acts as a subaction of the 1-1 action on S3 times S3. Okay, so and this is just a fancy way of saying, since the two rotational speeds are the same on both components, and since the order of this guy is equal to 2, this is just a fancy way of saying that this is rotating on the op fibers of this S3 factor with by angle 1/2, and it's rotating on the op fibers of the S3 factors in this topological cone by angle 1/2 as well. Okay? So what happens when we go through the induction? So what is the setup after step I of the induction. Okay, so the setup is going to be that we have built a manifold M bar I, and the manifold satisfies the following requirement. So it's going to have a boundary. This boundary is going to be diffeomorphic to S3 times S3. Okay, and this boundary is going to have a collar in particular, which is gamma I equivariant. And on this collar, the generator of the group capital gamma I, little gamma I, acts trivially in the radial direction. So the collar is going to be diffeomorphic to S3 times 0, 1. Okay, and with this identification, the generator little gamma I is going to act trivially on this component. Okay, and on the other end, it's going to act as a subaction of the action 1, 2 to the I minus 1 on S3 times S3. Okay, and so what does that mean? Okay, so pictorially this means that my manifold is going to have an end, okay, which is diffeomorphic to S3 times the complement of a smaller 4 disk inside the 4 disk. Okay, so this is the boundary S3, and here you see the collar. Okay, you need to take the product with an S3. Okay, so this is the picture of the end of M bar I. Okay, and to understand what this couple of conditions means, we need to recall that the generator little gamma I of the group capital gamma I has order equal to 2 to the I. Okay, so let's unwind the definition and see what that means. So the fact that the order of gamma I is equal to 2 to the I implies that gamma I acts, so let me denote this first condition as I1. It acts so as a rotation of angle 1 divided by 2 to the I on the first S3. Okay, so this is this component and this component. Here the guy is rotating with angle 1 divided by 2 to the I. Okay, and on the other end, it's rotating with angle 1/2 on the second S3 component. Okay, so how does the construction continue? Okay, so how do I get from I to I plus 1? Okay, here I'm guided by the toy model that we discussed before. Okay, so what I had to do was to pick 2 copies of the guys that I constructed at the previous step. Okay, stick something new on top of them and glue the old copies, attach them to the new guy. Okay, and I'm gonna do something similar. Okay, so I'm gonna pick 2 disjoint copies of M bar I with the action of gamma I. Okay, and a copy of S3 times D4. Okay, so this new copy of S3 times D4, which is the guy that I got at the base step, I'm gonna stick it on the top here. Okay, and on the bottom, I'm gonna stick 2 copies of the old guys whose boundaries are diffeomorphic to S3 times S3, and I'm gonna think that there is a collar here, okay, which I'm gonna use in a second to attach them to this new guy. Okay, and from the new copy, what I do is I remove 2 smaller copies of the 4 disk. Okay, and in this way, my new component has 3 boundary components. Okay, there is the one induced by the exterior boundary of the disk, okay, which is the one that I would like to keep for the next steps of the inductive construction. Okay, and there are the 2 components that I created by removing the smaller 4 disks. Okay. Okay, and I'm gonna use those, I'm gonna kill those boundary components by gluing in the boundary components of the guys that I got at the previous step of the induction. Okay? Okay, but before I can do that, I need to tell you how the new generator little gamma I plus 1 is gonna act on this new piece of the manifold. Okay. And for that, I'm guided by what I wrote here at the previous step of the induction. Okay, so I stipulate that gamma I plus 1 acts, well, again, trivially on the radial direction. Okay, and it should act as a subaction of the 1, 2 to the I action on the, let's say, angular components. Okay, and here what I'm defining is the action of the new generator. You should think on a collar of this new boundary component. Okay, so let's unwind this once more. Okay, so this implies that gamma I acts as rotation with angle I plus 1, 1. So the angle is 1 over 2 to the I on the first 2 to the I plus 1 on the first S3. Okay, this is this S3 component here. And as rotation with angle 1 divided by 2 on the second S3. Okay. So, but now remember the algebra of the group. Okay, so gamma I plus 1 to the power 2 is equal to gamma I. Okay, and the action of gamma I was already defined at the previous step of the inductive construction. So there is a consistency check that I need to make. So this implies that gamma I, which is equal to gamma I plus 1 square, acts by rotation of angle I prime 1. So 0. So 1 divided by 2 to the I on the first S3. Okay, and now, so here I got a rotation of angle 1/2, which means that if I take the square, the power 2, it's going to be a trivial rotation. Okay, and so now we need to compare what I wrote here. Okay, so here I had an expression for the action of little gamma I on these boundary components. Okay, and the guy was rotating with angle 1 divided by 2 to the I on the first component and angle 1/2 on the second component. While here, on the other end, so you see that the rotational angles, they are not the same. Okay, so here comes the issue. Okay, so the issue is that if I glue these old copies, the guys that I obtained at the previous step of the induction to the new one with the identity, this is gonna turn into an inconsistency. So for the action to be globally well defined, we need gluing diffeomorphism phi I, so going from this boundary component to this boundary component, such that the following diagram commutes. So let me write. So here I got S3 times S3, which you should think of as being the boundary of this guy. Then I got another copy of S3 times S3, which you should think of as being the boundary of this hole that I cut here. Okay? And then I'm going to the same boundary component here with the, let's say, 1, 2 to the I minus 1 action. Okay, here I'm moving with a different action, the action induced by this expression here, which is an action only rotating on the first component. So it's a 1-0 action with the notation that I introduced 20 minutes ago. Okay. And here I'm moving with the gluing diffeomorphism phi I. Okay, so so in order for this action to be globally well defined, I would like to find gluing diffeomorphism phi I such that the following diagram commutes. Okay, and here a series of issues arise. The first one is that so in principle, the existence of such conjugating diffeomorphism is not guaranteed. Okay, and even after you come up with the choice of this diffeomorphism, now, so you get new issues because when it comes to endowing the manifold with the metric with non-negative Ricci curvature, okay, let me finish by briefly addressing this. Okay, so once you're able to come up with a choice of diffeomorphism making this diagram commute, you get a well-defined smooth manifold, and you get a well-defined smooth action. Okay, now the issue is that in order to get even a well-defined metric space, so forgetting about the non-negativity of the Ricci curvature, you would like this diffeomorphism to be isometries between the metrics induced on the boundary components of your object. Okay, and it's easy to check that such diffeomorphism cannot be isometric with respect to the product of two standard metrics on this two manifolds. Okay, so here is where other subtleties come, but so I'm almost out of time, so I'll finish here. Thank you for your attention.
Thank you. Do we have questions? Actually, let me ask a question. So here, although you didn't finish constructing it, but I would suppose in the end you will get 7-dimensional manifold. But you also said I guess the case of dimension 6 is also implied here. Is there going to be some sort of boundary of this?
So the only difference, the only difference in the 7-dimensional, in the 6-dimensional case, is that you need to replace D4 in the construction with D3.
Oh,
Okay, and in the other steps, you need to replace obviously the 2-sphere with the 3-sphere with the 2-sphere. Okay, so this is the difference at the level of the topological picture. Okay, what happens is that the 6-dimensional counterexample is harder to construct because it's harder to endow it with the metric with non-negative Ricci curvature in the following steps of the construction.
and the action on the S2 is also going to be different from
It's going to be different, so it was notationally more complicated. This was the reason why I chose to stick to the 7-dimensional case. Okay, so in the 6-dimensional case, where the section is S3 times S2, you have two different actions. The action on the first factor is the op function that I introduced before, and the action on the S2 factor is going to be just a rotation with respect to a fixed axis.
So in the end, you will actually also get the Ricci upper bound on the manifold because it's coming from isometric to the locally isometric to the universal cover of this.
What do you mean precisely? I'm not sure I
So
understood.
you will also get the Ricci upper bound on the manifold that you constructed. Since
That's true. So the Ricci curvature is uniformly bounded from above on the universal cover and also on the quotient.
Like, can you see like the Cheeger neighbor theorem from this kind of construction? When you look at the limit in some sense, and then you get codimension for singular sets.
The point is that so the upper, in order to apply the Cheeger neighbor theory to the blowdowns of the manifold, you will need two conditions to be satisfied. So the first condition is that the manifold has maximal volume growth, because Cheeger neighbors theory applies to limits with uniformly bounded volume from below, and this is not the case for the counterexamples. Okay, and the other condition you will need is a uniform upper bound on the Ricci curvature for the rescalings. Okay, but for that to hold, you need the quadratic decay for the Ricci curvature of the manifold, which is not satisfied in our counterexamples.
Okay. Yeah. Thank you. Do we have other questions?
Get some appropriate metrics. So you say that it's not direct product metrics.
Exactly.
It's non-negative. So
Yeah.
how you get that metric? You write down the metric explicitly, or you
We write down the metrics explicitly. So what we need to do is so you would like rather than thinking that you glue the old guy straight away to the new one, you would like to do the gluing through a gluing neck. Okay, and this gluing neck is going to be diffeomorphic to S3 times S3. So this is S3 times S3 times the interval. So let's say that this is 0, 1. Okay, so and what you need to do is to build a metric on this neck. Okay, satisfying. So one way to resolve this issue is to build a metric on this neck of the following form. So you know it with the metric of the form dt square plus f of t square times g of t, where g of t is a family of metrics on S3 times S3. Okay, and this family of metrics should satisfy the following requirements. So the Ricci curvature at any time should be positive. Okay, and this gives you enough freedom so that when you write down this metric here, you can do suitable choices so that the metric on the neck has Ricci non-negative. Okay, so you need some room here in order to be able to make this metric Ricci non-negative. And then you would like the theta 1, 2 to the I action to be isometric with respect to all the metrics on the slices. Okay. Okay, and the last condition is that, so you look at the diffeomorphism, which is conjugating these two actions. Okay, you would like the end metric, so let's say that G0 is the product of two random metrics. Okay, and then phi is this conjugating diffeomorphism. You want the end metric G1 to be the pullback of G0 with respect to this conjugating diffeomorphism. Okay, if you can achieve that, then you can stick this neck at the top of the old guy. Okay, and then there is no issue anymore in the gluing, because when you change picture through the diffeomorphism, okay, you're gonna see a different metric here on the top. Okay, but it's gonna be isometric to G0 after you conjugate. Okay, in this way you fix both the issue of the well definition of the action and the issue of the well definition of the metric.
Any other questions? All right, let's thank Professor Semola again for the wonderful talk.